solving trigonometric equations. Okay, as we go through class this week, we're going to have 3 2-hour delays this week. All right, so class is going to be shortened quite a bit. Next week will be a normal week, but then the following week we have 2 3-hour delays and 1 2-hour delay. Okay, so last 3 weeks of April, we've got like 9 days of class. Okay, collectively. Time will be mostly spent in those days, at least this week and next week, solving trigonometric equations. Okay. Last class we kind of finished with this statement, but I'm going to start you guys with this statement. My goal for you is not to get really, really, really good at one style of trigonometric equations, because then you're going to suck at the next style that is presented to you without any instruction on it, right? Okay. What I prefer to do is give you as many different varieties that I can so that you have at least one example that you can go from to work on practice problems that are similar to that, right? A lot of these questions are much like your algebra, okay, your college algebra, okay? We had in college algebra, let's think about this. We have we had linear equations, right? We had quadratic, we had cubic, and then let's just say polynomial, which all of those are polynomial, right? Okay. But there were some special situations that we came across within these 3 that maybe were different than what would happen for a 4th degree or 5th degree or something like that. We have exponential, logarithmic, we had rational, okay? And those types of equations, when they are presented to you, when a linear equation is presented to you, you have a different procedure than what you have when a quadratic is presented to you, right? When you have a quadratic presented to you, you might have maybe a GCF, and that helps you factor. Maybe you can use the square root method. Maybe you use the product sum technique. Maybe you use AC method, right? Maybe you use the quadratic formula, correct? Okay, so a lot of so when we see a quadratic equation, there's a lot of different techniques that you might use in solving that. Okay? When I see a cubic, maybe I got a GCF, and then that GCF, once I factor that out, leads me to a quadratic that I can go and use those techniques, right? Polynomial, maybe I got a GCF, and hopefully maybe if I got a GCF, it can lead me to that, which can then maybe lead me to that. And if I don't, then I use, remember the P over Q stuff? Okay. So the style, I'm not going to get into these, but the style of the equation leads you down a route or a pathway that you use to solve it, right? Which is different per type of equation. Okay. When we get into trigonometric equations, we want to be able to recognize the algebraic structure of that trigonometric equation. If I can recognize the algebraic structure, it's going to classify as one of those things in there. Okay? And then I'm going to use what we've learned in college algebra, algebra 2, algebra 1 to help push ourselves through that trigonometric equation. Okay? So what I'm going to argue to you is that the first step or first 2 steps of every trigonometric equation will be recognize the structure, maybe substituting, that kind of thing. But when we do that, it should then generate something that is algebraic, college algebra, algebra 2, algebra 1. And we'll go off of that knowledge to get all the way to the last step of the trigonometric equation. And then we turn back to trigonometry to answer that last step or to finish that last step. Okay? So that kind of makes sense. So the bookends of the process are trigonometric, and everything on the inside then is algebraic. Okay, and that's what we're going to try to focus on with these questions today. But again, if I just gave you questions that were just always quadratic in nature after we do substitution, you're going to get good at those, but you're not going to get good at the other ones, right? Okay, so I'm trying to show you as many different styles as possible so you have multiple techniques and tools at your disposal. So the first one I believe I want to show you is tangent squared. And this is in the notes. I just don't want to scroll over there. It was tangent squared theta minus 3 equals 0. Tangent squared theta minus 3 equals 0. All right. Couple routes you can go. If you recognize this structure, you can leave it as it is. Okay? I recognize this structure here is quadratic, and because there is no first degree term here, I can use the square root technique or square root method. Okay? Some people might like to do this. If I let u equal tangent theta, what's u squared? Tangent squared theta. So then could I substitute and say u, could I replace that, right? U squared minus 3 equals 0. I like to use u substitution. I don't think you necessarily need to on this one, but at least gives you the visual that the trigonometric equation that we started with structurally is a quadratic in which you can solve using the square root method, right? Add 3 to both sides, take square root, correct? If I add 3 to both sides, we get u squared equals 3. Square root both sides then, I should get plus or minus radical 3, correct? Is everyone okay with that? But we're not solving for u. Remember, we're solving for tangent theta. Okay? And actually, the end result, the end goal is to actually solve for just theta. Okay? But u was tangent theta, so let's put that back in. And I'm just going to separate this. You'll see why here in a little bit. When I get a plus or minus, it makes sense to separate them as they're two separate components. Okay. Now, some of you might realize, well, I could have gone straight from here to these two things by adding 3. And I get tangent squared theta equals 3, right? And the square root both sides, you get tangent theta equals radical 3, tangent theta equals negative radical 3. And that's fine, okay? So you can bypass the u substitution. That's fine. But like I said, the u substitution, I think, gives you that structure, that visual of the structure that you're going to use to solve the problem. All right, so remember what we're trying to solve for. We don't really want tangent theta. We want theta. So how do I get that theta to come out of this function? I'm going to use the tangent inverse. Okay. And I'm going to use that on both sides, right? Should have given myself a little bit more room to write it, but when I do that, tangent inverse and tangent fall out. Okay. Now remember, they only fall out because of the assumption that we're making here that these two will only cancel provided that theta is between what two angle measurements? What was the cancellation rule? Yes, negative 90 to 90. That's the only time that we get cancellation with the tangent and tangent inverse. That means then when I ask the question, what is the tangent inverse of radical 3? The result that you give me can only be between negative 90 and positive 90. Does that make sense? Okay. Same thing here on the right-hand side when we take the tangent inverse of negative radical 3. Okay. Is everybody okay with that? We now have kind of the implied solution for theta. Okay. But that's not in the notation that we're interested in. Okay. Usually your problems will say one of two things. Solve for theta when theta is, I'll do this, solve for theta, and they'll say on the interval from, let's just say 0 to 360, or they'll say solve for theta on the interval from negative infinity to positive infinity, however they want to say it, okay? When they say solve for theta on 0 to 360, they could say 0 to 720 or 0 to 1080. They go negative 360 to positive 360, but they're giving you a starting value and a finishing value, or an ending value, right? What that means to us is that there's going to be a finite number of solutions. You'll be able to count how many solutions you have, okay? If they ask that bottom one, solve for theta on the interval from negative infinity to positive infinity, that means you're going to have an infinite number of solutions, right? And you cannot physically write all of those down, so we'll have to write an equation for those, okay? Right now, let's just, because in all of those, even if you're trying to do this, if you're trying to write the infinite number of solutions, you still have to do that first, okay? So my philosophy is always find your solutions on 0 to 360 first. Okay? No matter what they ask. Even if they ask me to go from 0 to 180 or negative 180 to positive 180. Okay? You're always going to find the solutions between 0 and 360 first. And then decide what do we do with them after we have them. So, couple ways of doing this. Okay? I'm a fan of using my unit circle. Okay? Or the knowledge I've hopefully obtained in the last month and a half of the unit circle and our exposure to it, to know that when I take the sine divided by the cosine, and the result is radical 3, that had to be an angle of how many degrees? How do I get radical 3 by dividing these sines and cosines? 60 degrees. It's a radical 3 over 2 divided by 1/2, right? The way I've always remembered this is that when I'm dealing with the tangent, there's only a few different results I can get from the tangent off the unit circle. Okay? 1, which is at 45, 45, 90, right? Okay, radical 2 over 2 divided by radical 2 over 2. I can get 0. I get undefined, I can get radical 3, I get radical 3 over 3. Okay? These all happen at multiples of 45. 45, this actually happens at 90, and this is going to happen at 0, right? Okay? This happens at 60 degrees, and this happens at 30 degrees. And if I look at those two, they're very similar, right? But one of them has another 3 than the other one does, right? And this, would you agree that has another 3 in comparison to the 60? So that's how I remember. The one with the most 3's goes with 30. The one with less 3's goes with 60. So I know that this is going to be 60 degrees right here. Okay? Now, just using our logic about, okay, well, how do I get negative radical 3? That means one of the sines or cosines has to be negative, right? And because I'm only looking between negative 90 and positive 90, the only way that could be is if the y value was negative, right? So if I go down to negative 60, that will also work. Is it okay with everybody? Now here's where we have to be thoughtful. Negative 60, if I type that in as an answer, is going to be wrong. Yes, so that because they predefined the interval that they want solutions to come from. So 0 to 360, and this is outside that interval. So what do I need to do with that to get an angle that is inside that interval? Add 362. So find a positive coterminal angle, right? So 300 degrees. Okay, so let's take a look at this real quick on, we'll do GeoGebra here. All right, so what I've got here at point A, okay? Point A, what I've done is to take it to 60 degrees is pi over 3, right? Okay. So working in GeoGebra just makes it, just things are so much easier in radians. Same thing on Desmos. You can do either of them in degrees. It's just adjusting scales and that kind of stuff's a pain in the butt. So we get that point A. Okay. Now I'm going to look at this point C here, and that is 300 degrees, right? Is that okay with everybody? Now, if I look at this, let's just say if x is between 0 and 2 pi, then show me that. We're missing some stuff, aren't we? We went by hand and we found 60 degrees and 300 degrees and said, well, those are the two places where we cross the x-axis. But if I graph it, there are actually two other places that cross the x-axis that we do not have. Okay? So we're going to find those. And this is the idea that our calculator doesn't always give us what we need, because remember, the calculator is using this idea that the tangent inverse, okay, is restricted between this negative 90 and positive 90, okay, for the theta. So this is how I do it. I think this makes the most sense to me. Okay, if you find another procedure that works for you, have at it. Okay, but this is what's going on in this problem. Okay, and it's all because we want answers between 0 and 360. The first answer here was 60 degrees. Let's say that's 60 degrees right there. And that was a solution because when I took the ordered pair of 1/2 comma radical 3 over 2, sine divided by cosine gave me this radical 3, right? Okay. Well, what will happen every single time if I take this terminating ray and find its opposite ray, which would be that ray right there? Does that make sense? Okay. How big would that angle right there be? 60 degrees. That's a vertical angle with the original 60. Does that make sense? Okay. That point right there, because of the symmetry, is going to be still 1/2 radical 3 over 2. But it's in the third quadrant. So it's negative divided by a negative, right? And what's a negative divided by a negative give you? Still that positive radical 3, correct? Okay, but this is in the third quadrant, which is not in between negative 90 and positive 90, right? So this is that extra angle that our calculator cannot produce for us. Okay? Now, that's 60 degrees, but we always talk about our angles from standard position, right? So that is really the theta that we're interested in. And that would be 240. Is that okay with everybody? So I'll say here that theta is not only 60, but it's 240 degrees as well. Okay? If we go over here, so 240 is what, 4 pi over 3? So we go 4 pi over 3, comma 0. There you get that point. Okay. Now, the other point that we're missing here comes from looking here where this is, so this was 300, right? Okay. I'm actually going to, I think it makes more sense to go up to negative 60 right now. But that, if I go that way, that's 300. If I go this way, it's negative 60, right? It's still the same terminating array. The reason I like to do that, if that's negative 60, now the idea of the opposite ray, careful. Because remember, if that's 60, okay, yeah, you could say negative 240. Okay, but we don't like an answer between 0 and 3. We want an answer between 0 and 360. So what do I do with that negative 240? At 362, it becomes 120, right? I like to that works every time. I like to do it this way where I see the vertical angles. Because now this was, remember, that was a positive 1/2 divided by negative, or sorry, it's a negative radical 3/2 divided by a positive 1/2, right? Up here, it's a positive radical 3/2 divided by a negative 1/2. So the SIGN changes from the numerator to the denominator, right? But is it still a negative quotient? Yeah. So now theta comes from that angle right there, which if it's 60 degrees short of 180, theta here is also got to be 120. Does that make sense? Okay. Which 120 then, just going to GeoGebra, check it out, and visually is 2 pi over 3. And you see there that we've got those 4 points, right? Okay. So those are the 4 solutions between 0 and 360. Okay. Or if we do it in radians, you have pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Okay. Now, if they define your interval that your solutions have to come from, you're going to write all 4 of those as answers. Does that make sense? Okay. If they ask you for the infinite solutions, it's going to be a little bit different. Okay. Basically what happens if I want the infinite solutions, and let's just right now look at 0 to 4 pi. Let's just go out one more interval here. I'm actually going to hide those 2 right now. Let's look at, actually let's hide that one as well. If I look at B, okay, and I'm going to make B, okay. So this point B right now, okay, all I've got it set up to do is take the x value from point A. Okay, the x value from point A, which is the pi over 3, which was the 60 degrees, right? It was the first solution that we found. And add to it pi, which what is pi for the tangent function? It's its what? It's its period. Okay? So I'm going to take the first solution, add to it pi. Okay? And when b, right here, this lowercase b is 0, right here, when the slider is at 0, it gives me that first solution, right? Well, when b is 1, it now gives me that solution. When b is 2, it gives me that solution. When b is 3, it gives me that solution, right? Does that make sense to everybody? And as that thing keeps going on and on in both directions, it's going to give me those kind of associated solutions. They associate back to what A was. Okay. Now, if I look at this point here, C. C is the 300 degrees, okay, or the 5 pi over 3, comma 0, okay. If I add pi to that, which is going to give me this formula here, so I take the x value of C, which was 5 pi over 3, and I add pi b to that, okay. So point D, when b is, so let's say b is, or lowercase b is 0, let's hide that one, let's hide that one. You see that's the same point that C was, right? Now when I move that through, it gives me those additional points, correct? Okay. Now, what I want to do here real quick is just show you all of these put together. When I put them all together, so right now, and we'll talk about this structurally as an equation here in a moment. If I start with A and C, which were the 60 degrees and the 300 degrees, and I add pi times an index value here, okay, does that end up giving me all my solutions? Does that make sense? Yes. Well, that's what we're going to talk about. Okay. So we've got on the interval 0 to 360. Okay. We found solutions for theta to be 60, 300, 240, and 120, correct? Okay. On the interval from negative infinity to positive infinity, the way we do this, we take this one here, we'll take 60, and we're going to add to it the period, and that will give me the next one, right? Okay. So that just moves it down the line a little bit further on the x-axis to the next intersection point. Okay. Now I could add 360 again, add 360 again, add 360 again. So I'm going to throw on a K here. Okay. Now the way I set it up in GeoGebra was a B, right? Lowercase b. It doesn't matter. They just use K in most instances. And we identify that K is an element of your integers. Okay? Which, remember, your integers are things like things all the way from negative infinity to positive infinity. No fractions, anything like that, right? Yes? Say again? Oh, I'm sorry. You're right. Should say, I was getting ahead of myself in the next question. Period for tangent was pi, right? So 180. I apologize. You're right. Okay. So now I'm going to take the next one and do the same thing. So 300 plus 180 K, where K is an element of your integers. The next one, 240. And what sign? Is that what you said? Yeah. It should tell you that, like it'll be very specific in the directions, and there should be I don't know if there's a box to type this in or something like that, but there's something. Okay. And if we're doing this on a handwritten test, you wrote all these, I'll give you full 100% credit. But you've written too much. Okay? You have to have all these if they ask you for 0 to 360. Okay? But these, there's some redundancy. Okay? If K here, let's say if K equals 1 right here, what does that give you? 240. Which will be the same thing that produces when K is 0. Does that make sense? So this solution set right here lags behind this one by an integer. So if this one was K equals 2, it's going to be the same result as if this one was K was equal to 1, right? Does that make sense? So this one is redundant because all the solutions that this one will create are created here. Okay? Doesn't really matter which one you get rid of. Don't really care. If you're not going to report both of them. Does that make sense? Okay. Now, if this one, let's say K here was 0. Then here, K would have to be -1. So this one here lags behind this one by an integer. Okay. So just keep that in mind as you're doing these, and the infinite realm, okay, in that type of solution set, there can be redundancy, and you just got to pay attention to that. I can't remember because I haven't done them in, like I've looked at them in WebAssign I haven't looked at them as a completed or solved problem. So I can't remember if they will accept you typing all of those in, or if they'll give you feedback that says you've got something to miss here. And I'm not sure what that feedback would be, whether they would tell you you're on the right track but you're redundant, or if they would just accept them. Does that make sense? It'll just be something you have to experience and see what they're looking for. If you type in the two basic, okay, if I type in 60 plus 180K and 300 plus 180K, they'll give you full credit for that. Okay. We cool with that idea? All right. Say it again. I can't hear you. Yeah, I think it would. Because so just as long as you don't use that one and that one, because they repeat the same thing, so then you'd be leaving out the solutions that are generated by those two. Let's do one more. Let's go 2 cosine squared. I'm going to write this on the side so it's cleaner. Two cosine squared theta minus 7 cosine theta minus 3, was it plus 3? Plus 3 equals 0. All right. The nice thing about this one is that the trig functions are the same function, right? Now it's cosine squared and cosine to the first, which is okay, but it's not like cosine squared and sine. If they were differing, and this is what we'll get into tomorrow in other examples, if they are differing trig functions, sometimes you'll try to make a substitution so you can make them the same. Sometimes maybe they differ because there's a GCF. So there's going to be different pathways that we go through if the trig functions are differing. Okay? But here, they are the same. And my hope is that you can see that there's a structure here. Okay? It's cosine squared, cosine to the first, cosine to the 0. That's quadratic. Does that make sense? And it's easier to see if we say let u equal cosine theta. So then what would u squared be? Cosine squared theta, right? So we make that substitution and we get 2u squared minus 7u plus 3 equals 0. Now, everything that we do up until the last steps of this is going to be strictly college algebra, algebra 2. Okay? So take a minute, see what you come up with as you factor that. So you guys get down to u equals 1/2 and u equals 3. Okay, and that's all relying on our college algebra, right? Okay, there's no trig there. Now, what was u? Cosine. So I'm going to make that substitution. Cosine theta equals 1/2. And then over here, cosine theta equals 3. Okay? Now I'm just leaving a little bit of a gap there because what are we going to do to actually solve for cosine? Or sorry, solve for theta. Yeah, take the arc cosine. So you go cosine inverse here, cosine inverse there. So that's going to give me theta. But what are we? The condition that has to happen here for theta to be the only thing left over for direct cancellation to happen is that theta is between what two numbers here for the cosine? 0 and pi. Okay, or 0 and 180 if we're thinking in degrees, right? And I haven't specified because I think we should be able to do it in both, whether I want to be in 360 or 0 to 360 or 0 to 2 pi. Okay, radians or degrees. Each question you do in your homework will specify before you do it what they want us to be in. Okay, so because you said 0 to pi, let's go ahead and do this in radians then. So then, on my unit circle, what is the angle between 0 and pi that will produce an x value of 1/2? Careful, cosine is pi over 3. Is that okay? All right. Now, let's just be thoughtful. Let's just continue this because let's say we want to go on the interval between 0 and 2 pi. That's usually the kind of the basic predefined interval that most of the questions will go with. Okay. Is there another angle that has an x value of 1/2 on the unit circle? It's got to be here, doesn't it? Which is 5 pi over 3. All right, because cosine is the x value, right? If that's 1/2 right there, then the other 1/2 is going to come, so it's got to be in the fourth quadrant. So you can say that's negative pi over 3, and then add 2 pi to that, and that gets you 5 pi over 3. Because I'm only using 0 to pi to tell me that I have direct cancellation, so my calculator is only going to give me the pi over 3. But if the question overall in the direction says find solutions on the interval from 0 to 2 pi, this one right here is on that interval from 0 to 2 pi. So I have to be able to find that. This interval right here, I'm only using that to justify this cancellation of the cosine inverse and the cosine. Come over here, take the cosine inverse. Cancel, cancel, gives me theta. And now where does the cosine have a ratio of 3? Never. Okay? Because remember, cosine is adjacent divided by hypotenuse, right? I can, no matter what my two values are here, the hypotenuse is always going to be the biggest, right? I will never be able to take something and divide it by something bigger and get 3. Impossible, right? Okay? So theta is undefined there. Really get no solutions from that component. Okay? So my two answers are pi over 3 and 5 pi over 3. Now if I want to find the infinite solutions, what do I do with that pi over 3? So I'm going to add the period times k and state that k is an integer. And then I'll add 2 pi k to the other solution of 5 pi over 3 and state that k is an integer. Okay? So your infinite solutions they're a canned or just a formatted or standard set of equations where you say theta is equal to original realized solution, which would have been the pi over 3 or 5 pi over 3, right? And then you add to it the period times k, and then state that k is an element of your integers. Now the period, remember, for sine, cosine, secant, cosecant is 2 pi, and for the tangent, cotangent, it is just pi, right? But that is the general format for finding your list of infinite solutions. Okay? All right, so we've seen one where we use the square root method. We've seen one where we use the AC method. Maybe tomorrow we'll see one with the GCF. Over the next couple days, we'll see one that we have to revert to the quadratic formula. Okay? Every one of them so far, our theta has been found by using the unit circle. Okay? But there's nothing that says that we can't get down to a situation that says cosine theta equals 3/4. And then we know 3/4 isn't a value that we know off the unit circle, right? It's there, we just don't know what angle goes with it. So we would have to revert to our calculator and let our calculator spit back what that angle is. Does that make sense? You can use your calculator to spit back the angles now as well, but hopefully it's quicker just to go from memory of the unit circle. Have a good one. Thank you.